All right, so here we go. Here's the conformation of butane. But first, what I want to do is kind of go over a little molecular model reminder of ethane. So remember, here's our ethane. We got two black atoms representing the carbon, and look, each of these three white ones is a hydrogen. So remember, C2H6, that's ethane. All right. So also remember that you can rotate about this carbon-carbon bond, and let's say we stopped here and we're looking down this carbon-carbon bond. We've got a hydrogen up here, and then we've got the nearest group that is visible when you're looking from this point of view is here or here. Each of these is 60 degrees apart, and this particular conformation is a staggered conformation. Right? We can also rotate 60 degrees to make sure that we kind of block out those hydrogens in the back as well as that carbon. And we've got an eclipse conformation, right? So let's say that I replaced each of these hydrogens for methyl groups. Okay, so let's see. What we've got here is failure. I just dropped my stuff. All right, so now what I did is I replaced these two hydrogens at the top with two more carbons. And so now what is this molecule? We've got 1, 2, 3, 4 carbons. 4 remember it goes methyl, ethyl, propyl, butyl, or bute. And so this is butane. This is the molecular model of butane. It's pretty cool stuff. As you can see, it's a lot more going on, right? It's a little more crowded. That's not cool, right? So bear with me when we're working with this. We're still looking down this carbon-carbon bond right here, okay? But now, remember how we had all of those chemical bonds, or I'm sorry, all of those hydrogens were eclipsed? Well, this is actually still an eclipsed conformation. But as you can see, these methyl groups are much bulkier, right? And so, since we have the presence of these methyl groups, we're actually going to introduce a couple different types of staggered groups, and then also we have different types of eclipse conformation as well. Okay, so first let's just go over what I'm talking about, and then we'll define a few things. Okay, so first, this is eclipse. Well, let's say we rotated it 60 degrees. So this is a staggered conformation, right? Well, this is staggered, and then as you go here, you can see that this is also eclipsed, but now this methyl group is a lot further away from this methyl group, okay? And then rotate another 60 degrees, and we've got staggered conformation again, but these methyls are pretty much as far away from one another as possible. And so remember when we were talking about hydrogens and the presence of those hydrogens, or I guess being in close proximity in an eclipse conformation, that actually raised the energy level of the ethane by 4 kilojoules per mole. So what do you think this is going to do, right? This is going to provide an additional increase in energy with having these hydrogens here, because as you can see, they're a lot bulkier, and so they're going to cause something called Steric Hindrance, which means basically there's not enough room for things, and so it's going to cause basically a strain. That's why it's called steric strain in the molecule. So, for example, I'm not sure if you can hear that, but these are so close that they're actually making a cool. You guys remember that toy? They were going beep, 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 super annoying. Don't ever give those to people with kids, by the way. But they are so close. They're in close proximity. That's kind of the idea of steric hindrance, or I'm sorry, steric strain. And since they are so close, if they want to get as far away from one another as possible, what they have to do is cause some kind of something's got to give, right? And so this bond is going to kind of be a little contorted to kind of push away from those electrons, the cloud or the methyl groups, so they don't bounce into each other, because that's obviously not good when you have two electron clouds kind of coming together to butt heads. They're negatively charged and they want their space desperately, right? And so we need to have these kind of be pushed out a little bit. And so this is the idea of steric strain. Okay, so steric strain is going to cause an increase in the conformation, increase in energy for this particular conformation. All right, so that increased energy for the conformation due to the steric strain is very specific to depending on the types of groups that we have. So for this, for example, remember for ethane when we had an eclipse conformation, eclipsing one hydrogen with another hydrogen increased the energy level by 4 kilojoules per mole. And we had 1, 2, and then we had 3 in ethane. And so that was 12 kilojoules per mole total. Now, being that we have methyl groups on this butane molecule, there's a different energy increase associated with the eclipse conformations. Okay, so what we want to do is go over the different types of staggered positions as well as the what am I looking for? Eclipse conformations. Sorry, and then we'll kind of tally those numbers up and see what we can kind of draw out for the dihedral angle and the versus the energy for butane. Okay, so first and foremost, this is an eclipse conformation, right? So is this eclipse conformation, where we got the two methyl groups right next to each other, do you think it's equal in energy to this eclipse conformation? Probably not, right? Because this methyl group is further away from this methyl group, yeah? So let's go back to this one. Look how close these methyl groups are. They're like boom, 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 right? So this increase in energy is very high, and it's this eclipse conformation when the methyl groups are eclipsing one another is an increase in energy by 11 kilojoules per mole. Okay, whereas this eclipse conformation is a methyl group eclipsing a hydrogen in the back. So that hydrogen doesn't really need that much space. I can't really spin it to make it knock into the other one, and therefore that energy increase or destabilization energy associated with this conformation is a little bit lower. It's still pretty high because it's 6 kilojoules per mole for this particular eclipse conformation, but it's not quite that 11 kilojoules per mole, which is pretty high. Okay, now these are pretty much the two, because if I rotate over here, that's the same as this one, right? If we're eclipsing on where the methyls on the left side or the right side, doesn't matter, okay? Those are equal in energy. And so now the other two staggered conformations that we want to introduce are as follows. So notice this is a staggered conformation. We've got a methyl group in between, kind of bisecting these two chemical bonds right here. And you can also see it maybe a little bit better with the hydrogens here, bisecting these two, okay? I'm trying to get it perfect, but it's not. Now, do you think that this energy associated with this conformation is equal to this energy, the energy of this conformation? Probably not, right? And if you guess that, then you are correct, because this methyl group is literally as far away as possible from this methyl group as it can get when being in the same molecule, butane. Okay, and so what we want to do when we're trying to draw our dihedral, our energy versus the dihedral angle for butane, is we want to call this our zero energy, because this is the lowest possible energy state of butane, because we have the two large groups being as far away from one another as possible, reducing steric strain, okay, and therefore having a more stable conformation, okay. Now, if we rotate 60 degrees, let's go this way, okay, we have an eclipse conformation that, again, is associated with how many kilojoules per mole? 1, 2, 3, 4, 5, 6, okay, and 6. So 6 kilojoules per mole for this eclipse conformation. And then we go here. This is it's another staggered conformation that is actually called gauche, Gauche. And this does actually, even though it is a staggered conformation, this methyl group is pretty close to this one, and therefore there is a destabilization energy associated with it. and it's 3.8 kilojoules per mole. So it's pretty low. This is staggered. This is gauche, okay? And this one right here is eclipsed, and there we go. This is 11 kilojoules per mole. I forgot to tell you that this conformation is called staggered anti. So it is staggered. This one's more specifically called anti because this methyl group is completely opposite of this one. And then this one is called gauche. Okay, so remember, eclipsed 11 kilojoules per mole for these eclipsing methyl groups only, right? So when we're going to tally up the whole thing, we still have to account for the eclipsed hydrogens on this side and this side. So remember, this is 4, this is 4, and then this is 11. So that's 11 plus 8, and that means that this particular conformation is 19 kilojoules per mole higher in energy than this staggered anti-conformation, okay? And then this one right here is got that 3.8, okay? And then this one right here has got that 6. But then we also have, so the methyl group eclipsing the hydrogen is 6. We have another one up here. So this is another 6, and then these hydrogens right here are 4. So that's 16 kilojoules per mole, and then again back down to 0. And so this particular diagram is going to look a lot different than the ethane, but it's pretty straightforward as long as you can kind of understand that there are different types of staggered positions as well as eclipsed positions, and the energy associated with the destabilization energy associated with it. Okay, so that's pretty much it. Let's hit the whiteboard and let's take a look at what these things look like. Okay. All right, so let's take a look at what these Newman projections are going to look like for a butane molecule. So first, what we want to do is draw butane with those dashes and wedges. So let's just go ahead and draw it like this. I'll put a CH3 there just for the sake of being very explicit. We've got our hydrogens here, and now we've got a CH3 here. I'm not labeling these carbons. Those are going to be implied. And then we've got our hydrogens there. Okay, so this is methyl ethyl propyl butyl. So this is the butane. All right, so let's say we are looking down this chemical bond right here. Yeah? All right, so what's that Newman projection going to look like? Well, since this methyl group is projected downward, our Mercedes sign is going to be a little bit flipped over. And we've got a CH3 there. We've got 2 hydrogens projected to the inward and outward in this particular with the wedges and dashes, and so we've got a hydrogen on the left and the right in our Newman projection. And now we got to look at the stuff at the back. Okay, so let's just label that stuff. That's blue CH3. We've got a hydrogen. All right, and so we've got boom, boom, boom. This is, since we've got this chemical bond and this chemical bond in the same plane but opposite of one another, this is a staggered conformation. And we've got the CH3 poking upwards, and therefore we've got our hydrogens on the bottom. So this is actually, this is a staggered conformation. Staggered, but this is staggered anti. Again, remember, because this methyl group and this methyl group are as far away from one another as possible, and then the energy, the relative energy for this is equal to 0. I'm going to put relative energy is equal to 0. Okay? And now, we're going to basically have to draw out all of the different Newman projections to kind of give you an idea, and then what we'll do is translate that into an energy diagram, as well as kind of reiterate what those new strains are. Okay, so and first what we want to do is rotate 60 degrees. Now, depending on how you want to do it, let's go ahead and just remove the back stuff 60 degrees to the right. So what that's going to do is leave the front the way it is. Here, let me draw a circle. I don't like it. I don't like it one bit. Wow. I can't draw on an iPad. Usually my circles are perfect. Here, I'll do this. Woo. All right. Cool. I'm going to cheat. Let technology do it for me. Now what I've got is this particular... Oh, look at that. That looks gorgeous. Actually, it doesn't look that good. Anyway, now, well, since we rotated 60 degrees, 60-degree rotation, we have our methyl group and our hydrogens that are in the front in the same spot, but now we've got our other stuff in a different spot. So I'm going to leave these guys here, and I'll put this right here. So all of those things in the back were blue, so I'm going to continue to leave that there. Our methyl group is now here, and then our hydrogen is here. Okay, and now this is also going to be an eclipsed confirmation. Okay, and then the relative energy associated with this is, remember this right here is an eclipsed methyl hydrogen, and that is 6 kilojoules per mole. And this is another one, so that's 6 kilojoules per mole. And this is eclipsed hydrogens, and that is 4 kilojoules per mole. Okay, so that's 12, that's 16 kilojoules per mole, higher in energy than the staggered anti-conformation. Okay. Well, all right, so let's say we rotated, so rotate 60 degrees again. Now what we're going to do is bring that methyl that's in the back, oops, not that far, just 60 degrees, folks. Come on now, simmer down. All right, so let's draw a circle. I'm going to cheat again because it works so well. All right, so remember we're leaving our methyl and our hydrogens that are in the front in the same position as they were. Okay, and now what we've got is another staggered conformation, and so our our methyl group is now very close to the other methyl group. You can see this right here. And remember, this is called the staggered gauche conformation. Gauche. Okay, I know that's weird, but hopefully you watch the video before you start reading. And it's pronounced gauche. And remember that energy associated with this was actually 3.8 kilojoules per mole, and this was due to steric strain. Okay, and so that's basically the relative energy. Relative energy is equal to 3.8 kilojoules per mole, because everything else, this part of the molecule, is staggered hydrogens, and that is relatively, relative to everything else, is 0 degree or 0 energy. Okay, and so again, remember we're writing relative energy because this is when compared to the staggered anti-position. Okay, so let's go ahead and rotate 60 degrees again. So what that's going to give me is another perfect circle. Let's move that over a little bit. All right, and I'll draw it like this. Our methyl and our hydrogens are going to stay in the same position. And again, you can rotate however you want. If you choose to put your methyl group on the top and then rotate from there, or rotate the front molecule instead of the back molecule, that's totally okay. You are free to do what you want. I'm just drawing it this way. Okay, and now since we were just in the staggered position, and if we wanted to rotate 60 degrees from, that puts our methyl group right on top of that other methyl group. And I'll make sure that I'm recording those in blue, so we're kind of sticking with the theme. And this right here is an eclipsed Confirmation. I didn't draw it in blue. I feel like I need to draw it in blue. So let's get that to blue, because Alright, and so the relative energy associated with this one is, think about it for a second before I write it down. And this is 4 kilojoules per mole. These are 4 kilojoules per mole. And this right here is 11 kilojoules per mole. So that is overall 19 kilojoules per mole, higher in energy than, again, the staggered anti-conformation. Okay. Now, let's say we wanted to rotate 60 degrees again. Okay. Now what that does is get that circle again. All right. Put that methyl on the bottom. All right, and so if we rotate this 60 degrees, what that does is it puts us in another staggered conformation. And CH3, hydrogen, hydrogen. And remember, this is a staggered gauche. Okay, so we still haven't made our way all the way around yet, because remember, this methyl group needs to be up here to get back to the staggered A&T position. So we're going to keep going until we can complete that cycle, because that will allow us to kind of get an idea as to where or what our energy diagram will look like, because we're summing up all of the energies. Okay. Now, this staggered gauche conformation has a relative energy of, since we just did it up here, it's actually the same. It's 3.8 kilojoules per mole for a staggered gauche, and that's because those staggered hydrogens don't provide any increase in energy or any destabilization effect. Okay. Now, let's see. Let's go to the right. Why not? Let's rotate 60 degrees. That gives us a circle here. Let's get that a little bit bigger. And now, my hydrogens and methyl stayed in the same spot. And since this was staggered, now what we're looking at is an anti-conformation where, since this was the staggered gauche conformation, now what we're looking at is an eclipsed conformation here, and so this is eclipsed, and the relative energy is going to be the same as this one right here. Okay, we can sum them all up again though. Let's see, how did we get to that energy? Well, that's a methyl and a hydrogen eclipsed bond, and so that is 6 kilojoules per mole. These are 4 kilojoules per mole, and this right here is another 6 kilojoules per mole, which is 12 plus 4 is 16 kilojoules per mole, higher in energy than that staggered anti-conformation. One more 60-degree rotation gets us back to our staggered anti-conformation. Okay, so let's draw that last thing. And we'll be done, and then we can draw our energy diagram. So there's our hydrogens, there are the methyl, or the methyl, and let's draw these in blue. We've got our hydrogens on the bottom and our methyl on the top. This is we are back to staggered anti. So the relative energy, remember, is always compared to this, and so this is equal to 0. Okay? So basically what we did was we went from 0 to let's see, we went from 0 to 16 to 3.8 to 19 to 3.8 to 16 back to 0. Let's see if I can do that. I can't do that. What did I just say? Alright, so we are going to 16 to 3.8 to 19 to 3.8 to 16 back down to 0. Hopefully that's right. Let's see what that would look like in a energy diagram. Oops, sorry. And here we go. So this is going to be our our energy versus dihedral angle for butane. Okay, so energy versus dihedral angle for butane. And so remember, I'll just draw something out really quick. For ethane, it looked like this, where basically we had one energy maximum and one energy minimum. Okay, and you've already seen the relative energies in butane, and so you know that there is not just one energy maximum or one energy minimum, or I guess there is technically, but it's not just 2 points that are on the graph where we go top to bottom. And so what I mean by that is, let's start at, let's see, so this is energy. And let's just start by drawing these points on the graph. So let's just say this is the 0 point, and then we go up to 16. This doesn't have to be perfect. We're not, nobody's perfect, right? All we know is that this is higher than 0, right? And then we know that 3.8 is lower, but it's not quite 0, so we're going to go here. And then we're going to go to 19, which is higher than 16. And then we're going back to 3.8, which has to be the same as that one. And so we go there, and then we go back to 16, which has to be the same as that one. And then we go back to 0 at the end. Okay. All right, so let's connect the dots. Basically, what we're doing is looking like this. Okay. And if we are kind of basing our dihedral angle based off of, like, with respect to these methyl groups, these are 180 degrees apart, right? And so let's do that. And so this point right here would actually be 180 degrees. And if we rotate 60 degrees, we are getting closer to 0. So that's 120 degrees. That's another, that's 60 degrees. And then this maximum energy, so this is max energy. This is equal to the the Eclipse Confirmation where the methyls are. Let's go back. It is right here. So this is the Eclipse Confirmation where the methyls are lined up exactly behind one another, and that's why we have that dihedral angle of 0 degrees. Okay? And that means if we continue to rotate, we're going back up to 60 degrees away, and then 120 degrees, and then 180 degrees, which completes our rotation. Okay. So again, let me do this. So max. Let's circle that. Change that to blue. So we can see that it's kind of something we want to point out. Another thing I also want to point out is the kind of the local minimums here and here. So this is the staggered anti, and then this is gauche. This is also gauche. And that's our staggered anti again. Okay, now these are our local maxima, and this one right here, I mean, they're all eclipsed, so there's not really much to write out. I don't want to label it as anything specific other than eclipsed. Okay, and then this one is eclipsed. But we have to know that the energy difference is because the location of that methyl group is either right on top of the other methyl group or kind of just right on 120 degrees away from it. Okay, and so again, this energy right here, I'll do, whoops, sorry, right here is 16 kilojoules per mole. This energy right here is 19 kilojoules per mole. And then back here is another 16 kilojoules per mole. While our gauche, let me erase these arrows, is 3.8 kilojoules per mole. And 3.8 kilojoules per mole. Okay? And that is our energy versus dihedral angle for butane. So let's sum up our types of interactions with our increase in energy. So if we have an HH eclipse bond, eclipsing, then that means we have an increase in energy by 4.0 kilojoules per mole. Okay, so let's do this. Type of interaction. And we have our energy increase. So you might see it in kcals per mole also, but I kind of will basically just be discussing these in terms of kilojoules per mole. But if you want to kind of convert, the conversion for kcal, or you can kind of refer to your book as well. Okay, so let's see if we can kind of make this nicely divided. We've got a hydrogen and a methyl eclipsing, and that is 6.0 kilojoules per mole. Okay, and we've got a methyl eclipsing, and we've got that's 11. I don't know why I don't like that, but 11 kilojoules per mole. And then the last one is gauche. So that is a gauche CH3 groups. And that is associated with an increase in energy of 3.8 kilojoules per mole. And there you go. This, remember, this is basically torsional strain, and this is steric strain and steric strain, as well as steric strain. So, I mean, you can honestly think of them as similar, right? Torsional strain and steric strain, or steric strain causing torsional strain, and but they are kind of distinguished in that the hydrogen-hydrogen eclipse bond is torsional strain, whereas larger groups like a methyl group and something else are associated with steric strain. Okay. Okay, and so one more thing I want to add about this type of diagram is another vocabulary word, and that is basically the difference in the energy associated with the maximum and the minimum. So since this from 0 to the top is 19 kilojoules per mole, that means in order for butane to kind of rotate around, it has to overcome an energy barrier, right? And that energy barrier costs 19 kilojoules per mole. And so this is, I guess it'd be better to write it over here, but this is the barrier to rotation. Okay, and this is equal to the energy difference between the highest energy state, between high energy state and the low energy state. Okay, and so for this one it is, in fact, 19 kilojoules per mole. And so that's going to be called the barrier to rotation, or the rotational barrier. Okay, so I think it's time for it. What do you think? Time for practice? You want to talk about practice? All right, let's talk about practice. So I'm going to do one problem that you should already know the answer to technically, but we're going to show you basically how to walk through it. That way we can kind of apply that to an additional problem following that, okay? And so let's take a look. Torsional energy in propane is 14 kilojoules per mole, and so that means that the maximum energy in terms of the Eclipse Confirmation is 14 kilojoules per mole. And how much is one hydrogen methyl eclipsing interaction worth in destabilization? Okay, so I'll draw this out while that ice machine gets a little crazy. All right, there you go, ice machine. Let's get all that anger out. That's cool. All right, so let's see. So, well, let me just draw your propane out first. Sorry, this is CH3, methyl, ethyl, propyl. Right? Sorry. This is a carbon. Wow, I'm just doing that all wrong, aren't I? Let me do this. How about this? Start here. Let's look down this chemical bond right here. So we're looking down that carbon, which means that we should explicitly draw our hydrogens here, and then our hydrogens here, and here, and here. Okay, and so remember this is a CH3 as well. So if we're looking, down this direction right here, that CH3 right here is on the bottom. We've got two hydrogens here, and then we've got our other hydrogens in the back. Okay, so this is the lowest energy state, but if we were going to rotate it 60 degrees, what we would end up with is, or I guess, yeah, let's just do right here. Keep the methyl in the same spot, just because, and that puts our hydrogens here and here. All right, so this is the highest energy, and according to the problem, it says that the energy associated with it is 14 kilojoules per mole. So what do we need to do? Well, what we need to do is kind of eliminate what we know. So we know that these eclipsed hydrogens interaction cost 4 kilojoules per mole each, right? And so that means if we subtract the 8 kilojoules per mole, that leaves us with 6 kilojoules per mole for this particular interaction, okay? All right, why do I care about that? Well, because I want to give you a harder problem. something that you haven't seen before, something that I didn't already technically give you the answer to. But this is also how we actually came to these conclusions. We can calculate these things based off of what we know, right? And so if we have a molecule like this, CH2Cl, and it equals 15 kilojoules per mole, less than the staggered conformation when it's in the eclipse. How much is the hydrogen chlorine eclipsing interaction worth in destabilization? All right, so what that requires us to do is draw this out. So we've got a carbon-carbon bond, and let's just go ahead and draw out at least something that we know. So this accounts for that group. Now we've got to account for the other group. Okay, so since we are technically looking down this chemical bond, we're looking that way, right? All right, so let's go ahead and draw a perfect circle. Yeah. And all right, so that hydrogen is actually up. And there we go. Let's see, now we've got our chlorine, our other hydrogen, and our other hydrogen. Let's go ahead and draw these bad boys in red so that way we can see them. All right, and so again, how do we do this, right? We know that this is 4 kilojoules per mole. This eclipsed interaction is also 4 kilojoules per mole. So what's that? Well, we're looking at 15 minus 8, which is 7 kilojoules per mole. Okay, and that's because chlorine is a larger atom than hydrogen, so it's almost double the destabilization energy. Okay, and these types of questions are going to be definitely seen, and they're pretty common, and they're nice questions to ask because it requires you to know not only how to draw a Newman projection, but the energies associated with certain, interactions. So the eclipsing and gauche interactions, for example. And so, yeah, there you go. That's a good one right there. Another type of problem is basically kind of tallying up, like which one is higher energy and which one's lower energy. Okay, and so in other words, what I mean is rank the following conformations in order of increasing energy. Okay, so all right, what I'm going to do here is draw a circle. Oh, you saw that? My computer, or my iPad hates me right now. It's trying to make squares out of circles. All right, so I'm gonna, just because I want these all to be the same, we're going to copy, paste, and then we're going to paste again. And then we're going to paste again. Ooh, I like how you lined that up. Let's do that again. All right, cool. So let's check it out. Let's draw our first one. And I ruined it with an off-centered placement of that central carbon, but it's okay. Otherwise, it looks pretty pretty. Oh man, too close. The struggle is real right now, guys. Come on, huh? I know you're feeling me right now. Drawing these things out is pretty tough sometimes. I have like years of experience. So I can only imagine where you're at right now. But there's one structure right there. It's gorgeous, right? Now what we want to do is draw another one. And then we'll kind of see where the relative energy is. And then we'll go from there. So CH3. CH3. All right, so this one is me drawing it as, here, let's draw it extended, okay? Because this is an eclipsed bond, CH2, CH3, okay? And then I might as well just draw that one extended as well. That's a hydrogen. And then I'm going to keep this one short. This is a CH2, CH3, okay? This is gorgeous, guys. Come on, just agree with me. It looks good. It's all good. It's all good. All right, so this will be compound A. This will be compound B. We're about to draw compound C. Here we go. Here we go. This is a methyl. Sometimes drawing these things out can be quite confusing because just the overlap, especially when you're drawing those eclipsed bonds. I'm going to draw this one extended here, CH2, CH3. Keep it similar. Draw that one extended. Let's see here. We've got our hydrogen here on the. Oh, let's fix that one. Let's draw it. Bottom. And CH2, CH3, CH2, CH3, hydrogen on the bottom. We've got our hydrogen here, the hydrogen, or I'm sorry, a methyl here, as well as another methyl here. So this is compound C and D. And remember, what we want to do is rank the following conformations in order of increasing energy. So first of all, let's take a look and see if what the similarities are. So is this even the same compound? Are we going to be able to do that? So what we have here is the central carbon should be the same. Okay, so what we want to look at is what's sticking off of that. We have a CH2, aka an ethyl group, ethyl or ET. Okay, just to kind of throw that out there. There's another ethyl group on that carbon. Okay, so what I would do is let's look at the compound B. Well, we do have an ethyl group. It's in the back, notice, and in the back we also have another ethyl group. Okay, sorry, on that same carbon we have a hydrogen. Okay, now let's take a look at the compound C and D. We've got a methyl or an ethyl group in the back with the hydrogen. We got an ethyl group in the front with the hydrogen. So all of those red ones are the same group. Let's take a look at the other ones. We have a methyl hydrogen. So that's a methyl hydrogen, methyl hydrogen, methyl hydrogen. And why did I do this? This is going to allow us to kind of make sure that we're comparing the same compounds and to get our minds right to see kind of if some of these are going to be maybe equivalent in energy because of the orientation, or kind of organize our brain in terms of the steric hindrance or torsional strain that is going to kind of come along with this. Okay, so I'm going to delete those just because it's too cluttered. I don't like it. All right, so let's see. First things first. Are any of them eclipsed or staggered? Yes. Okay, that's how I would classify them. So this one right here is staggered, right? It's some kind of staggered, and we don't need to classify it further right now. This is also some kind of staggered. And this one right here is some kind of eclipsed. And this one right here is also some kind of eclipsed. So we know that staggered, what are we supposed to do? We're supposed to write them in an order of increasing energy. So we know that A and D are going to be lower in energy than B and C. Okay, so let's try and figure out which is lowest in energy, A or D. All right, so basically you want to see what the interactions are. So remember, when we have like a methyl interaction with a methyl interaction that's in a staggered conformation, that's a gauche conformation. And so that means that even though they are both staggered, they're not necessarily going to be equal in energy. And so, for example, a methyl interacting with the hydrogen is technically going to be associated with 0 energy, relative energy. And so that means that the only energy that's going to cause an increase in destabilization is this interaction, as well as this interaction. We don't need to know what that value is, we just need to know that it exists. That's 2 different interactions that increase that energy. But if we look over here in A, we have that same interaction here, and we also have that same interaction here, right? That methyl interacting with the ethyl. But we also have an additional interaction that is a methyl interaction with another ethyl, okay? So if that's basically the way you want to walk yourself through this, is look at all of the interactions that these groups are going to have. And so A has more steric strain than D. Okay, so that means that D is the lowest in energy, followed by A, and now we need to classify our C and B. Okay, so same way, right? So we know that we have a specific energy associated with a methyl and a hydrogen, or an ethyl and a hydrogen, and an ethyl and a methyl. Okay, so let's take a look at the other one and see if it's clear. Basically, what I would do is try and cancel things out to see if there's a net difference. Okay, so let's look at the more drastic one. We have a methyl and an ethyl interacting. That's a methyl and an ethyl interacting, so that kind of cancels out. Now we also have another methyl and an ethyl interacting here, but we don't have that on the other compound, right? And so we do have an ethyl with a hydrogen and a methyl with a hydrogen, but that's not bad in terms of steric hindrance. This ethyl group is very large, and that methyl group is large, and so that's probably going to contribute a larger steric strain or destabilization. And so what I would put is B is more stable than C. Alright, I'm going to leave you with 2 amazing jokes. Actually, I'm going to leave you with 2 jokes this time because they're not really amazing, perhaps. But how many tickles does it take to make an octopus laugh? 10 tickles. Ha ha ha. Yes, yes, 10 tickles. Alright, the other one is, how do you get a squirrel to like you? You act like a nut. I don't know if that squirrel likes that one, but I kind of like that. Dad Jokes 101, that's what's up. Alright, have fun. Practice this stuff like your life depends on it, because maybe it does.